is used in situations in which we are interested in several dependent variables simultaneously, as opposed to just one dependent variable. It can be used when there is only one independent variable or when there are several, and we can look at the interactions between the independent variables, and we can set the contrast to see which groups differ from each other. The reason why MANOVA is used instead of multiple ANOVAs is because the more tests we conduct on the same data, the more we inflate the family-wise error rate. In other words, the more dependent variables we measure, the more ANOVAs we would have to conduct, and the greater the chance of making a type 1 error. Also, MANOVAs, by including all dependent variables in the same analysis, take into account the relationship between the outcome variables. It incorporates information about several outcome measures and therefore informs us of whether groups of participants can be distinguished by a combination of scores on several dependent measures. While all of this seems wonderful, sorry, we wish we had made buffalo chicken dip. While all of this seems wonderful, it's important to keep in mind that you should not lump all of your dependent variables together in a MANOVA unless you have a good theoretical or empirical basis for doing so. The MANOVA takes into account several dependent variables simultaneously by using a matrix that contains info about the variance accounted for by each dependent variable. The MANOVA calculates underlying linear dimensions of the dependent variables, which are known as variates, in order to predict which group a person belongs to. So they are used as discriminant function variates, which are used to discriminate groups of people. And you'll see me run that test. The MANOVA has the same assumptions as an ANOVA, but you must also check for the assumption of multivariate normality, which can be done using the Shapiro test, and equality of covariance matrices, which is often done using a boxes test. The effect of violating the equality of covariance matrices assumption is unclear, which is kind of comical. My research topic is concerned with different types of goal setting and their effects on organizational commitment scores, task performance scores, and employee satisfaction scores. I believe that the new goal setting system, which is done on the computer, is better than the standard method for goal setting, which is by writing everything down with pen and paper, and also better than not setting any goals at all. I'm looking at the effect of the goal setting system on my which is also my independent variable, on the average values of my several dependent variables, such as employee satisfaction, task performance scores, and organizational commitment. These dependent variables were measured after 4 months of using each method and were all measured on a scale of 1 to 20. My Group 1 completed computer goal setting, Group 2 completed paper and pen goal setting, and Group 3 did not set any goals. Within these groups, all participants had employee satisfaction scores, task performance scores, and organizational commitment scores measured. A MANOVA procedure allows me to test my hypothesis for all 3 dependent variables at once, so that's why I did it. So as always, we start by downloading the necessary packages, which I've already done, so I'm not going to show you, but I've probably libraryed these in the past, but I have them all written here for your benefit. The CAR package is used for looking at type 3 sum of squares. ggplot2 is used for graphs. MASS, which is new to us, is used for discriminant function analysis. MV outliers for plots to look for multivariate outliers. MV norm test is used to test for multivariate normality. PastX, as always, is used for descriptive statistics. Reshape is used for reshaping the data. And WRS is used for robust tests, which I do not conduct. I libraried them so I could have them in the future. I'm going to show you, it doesn't take as much time. Okay, now I chose to enter my data directly into R because of the manipulations that needed to occur in order to reach the desired covariances that our assignment requires. First, I created a coding variable by specifying that I was going to have 3 different groups with 12 participants in each group with a different label. So right here. So group 1 is called pen and paper, which is the group that made the goals on pen and paper. Group 2 is called computer, which is the group that made the goals on the computer. And group 3 is NGS, which is no goal setting. Next, I created the 3 numeric outcome variables by typing in the exact numbers that correlate with each outcome variable. So here's the employee satisfaction, task performance, and org commitment scores. Then I merged all of the created variables, so group, employee satisfaction scores, task performance scores, and organizational commitment scores into one data frame right here, which is what we use throughout. I made sure that the computer was aware that my group variable has 3 levels with the appropriate group names in order. I then did a summary of the data just to make sure it had been entered correctly. So here's where I did the group levels, and here is this to make sure that it was entered correctly, which it was. Next, I look at the descriptive statistics for each separate group. The first line of code gives a resulting output for employee satisfaction, right here. The next is for task performance scores, and the next is for organizational commitment scores. These outputs tell us the medians, means, etc. for each group related to the outcome variables. It tells us that pen and paper setting of goals and no goal setting both result in the highest employee satisfaction scores. And we know that because we go up here to employee satisfaction scores. And pen and paper and no goal setting have a mean of 9.25. Computer setting of goals and no goal setting result in the highest task performance scores, which is right here, these two. And computer setting of goals, and no goal setting results in the highest organizational commitment scores with a value of 16 right here. Next, I get the variance covariance matrices for each group by using the by function in combination with the COV function. The number 2 and 4 are used to tell R to use columns 2 through 4 from the dataset, which contain my variables employee satisfaction scores, task performance scores, and organizational commitment scores. And then R splits the output by the variable called group. The diagonal elements of the output represent the variances for each outcome measure, and the off diagonals are the covariances, or the relationships between employee satisfaction scores, task performance scores, and organizational commitment scores. The variances for employee satisfaction scores are a little different across groups with values of 0.93, 0.88, and 1.11. Which we see right here, and right here. So you're looking to see employee satisfaction line up with employee satisfaction. The variances for task performance scores, you look at it the same way, and it has one that's different with a value of 0.63 and two that are the same with 1.52. And then again, the variances for organizational commitment scores are 0.61, 1.48, and 1.54. As far as the covariances are concerned, for employee satisfaction scores and task performance scores, so you're going to look in this spot right here for all three. The values are negative 0.16, 0.52, and negative 0.64 for employee satisfaction scores and organizational commitment scores, which is in this spot. The values are negative 0.45, 0.23, and negative 0.02. And for task performance scores and organizational commitment, right here, the values are 0.3, 1.0, and 1.15. There's evidence to suggest that the matrices are different across the groups, but because we have equal group sizes of 12, we aren't going to worry about it. If we had different group sizes, then we would have to remind ourselves that if the larger samples produce greater variances and covariances, then the probability values will be conservative, causing the significant findings to be trusted. And if it is smaller samples that produce the larger variances and covariances, then the probability values will be liberal, and so the significant differences found in the MANOVA would not have been trusted, or at least they could have been trusted, but they would have been treated with caution. Now, due to this requirement of the assignment, I look at the correlations between each of my output variables. I first created the variable which told R to look at the correlation among my output variables and then ran the created variable to see the output. My task performance scores and organizational commitment scores are my high correlation with a value of 0.708 right here. And my variables of organizational commitment scores and employee satisfaction scores are my low correlation with a value of negative 0.09 right here. So I satisfy the requirements of the assignment. And where am I? Right here. The final assumption that we need to test is multivariate normality. We do this using the mshapiro.test function in the mvnormTest package, or the multi-outlier normality test. We want to apply this to the groups individually, so we have to first extract the data for each group. To get the pen and paper group data, I create a variable called P&P right here. And that's a subset of my data frame, and the square brackets used to indicate that I want a selection of the data. The 1 to 12 indicates the rows that I wanted to select, and 2 to 4 indicates the columns I want to select. I then have to change the format so that my output data appears in rows rather than columns, and the participants appear in columns rather than rows. This is done using the transpose function, which is not done until... Okay, so right there's the transpose function, but later on I do it all in one step. This is done using the transpose function of t. For computer goal setting and no goal setting, I combine these two steps into one, like I just said. I created the variable for the data I wanted to extract and then transform the data into the appropriate format. So right here was when I did it for the P and P. I did the create the variable, then I transposed it. Here's where I do it for computer setting and did it all in one step, and then no goal setting all in one step. I then ran the M-Shapiro test to test for multivariate normality of each of the extracted data sets. If the p-value is less than 0.05, then it tells me that my data deviate from multivariate normality. For pen and paper, which I'm running right this second, I got a p-value of 0.03, which means that the data deviates significantly from multivariate normality. For computer goal setting, right now, a p-value of 0.06 was reported, which means that there's no problem because the result is non-significant. And for goal setting, I got a value of 0.03, which means that the data deviate from multivariate normality. Next, I look at the outliers using the aq.plot function from the MV outlier package. I enter the columns of the data frame containing the outcome measures, so 2 through 4, and a plot for the current data is produced, which you can see. By using a comma, I tell R to select all of the rows possible, and by using 2 through 4, I tell R to select only columns 2 through 4, which are my outcome variables. The resulting plot showed that the row numbers in the data frame, and I am looking for the values in red in all but the top right graph. The plots tell me that there are no outliers because no numbers are reported in red for this one, and this one. If there had been an outlier, it would have been in red. For the top right graph up here, we look at the numbers to the right, the vertical line labeled 97.5% quantile, which so there would be a line here and it would be over here, and you would be able to tell that it was an outlier. It would correspond with the numbers that were in red. Again, it does not identify any numbers as being outliers. If there had been outliers, I would run a robust MANOVA. So next I had to set contrast because I hypothesized that computer goal setting and paper and pen goal setting would result in higher scores for my outcome variables than no goal setting at all. My first contrast compares no goal setting versus both computer goal setting and paper and pen goal setting. And my second contrast compares computer goal setting versus paper and pen goal setting. I then binded the contrast together and checked the created variable to make sure the contrasts were set correctly, which they were. There are several outcome variables, so first I had to bind the variables together into a single entity, right here. My single entity called high correlation was composed of task performance scores and organizational commitment scores because they are highly correlated. I also created a single entity called low core, which had an organizational commitment score and employee satisfaction score variables because they have a low correlation. I then created a model for the MANOVA called goal model, which is my highly correlated variables, and then predicts the object called high core, which is the task performance scores and organizational commitment scores from the independent variable of group. So I had to bind these together because we're doing a MANOVA on our high correlated variables and the one on our low correlated variables. So this just puts them together in one variable. And now here's where I'm actually creating the model for the MANOVAs. And goal model had the high correlation variable I created. So I'm going to run that. And now I also created a model for the MANOVA called low core goal model, which has my variables with a low correlation and predicts the object called low core, which consists of organizational commitment scores and employee satisfaction scores. To see the output, I did the summary command, which by default R produces the Palais trace. That was so not how I say it, sorry. Palais, something. The group effects are of interest because they tell us whether or not goal setting methods had an effect on the employees. We are interested in the column containing the significance values of the F ratio, which is 0.05 for the highly correlated variables, right here. And now for the low correlated variables, it is 0.03. So the highly correlated variables are not significant, which means there are no group differences, but the lowly correlated variables are significant, which means that there are group differences. So for the model with the highly correlated variables, the type of goal setting had no effect on the employees, but an effect was found to be present when looking at the model with the low correlation variables. Oh, goodness, let me get some water. Next, I follow up the analysis with univariate analyses of the individual outcome measures. I use the summary.AOV function, right here, to see the results for the ANOVA summary table for the dependent variables. The first model is for the highly correlated variables of task performance scores and organizational commitment scores. The parts we are most interested in are labeled F value and PR is greater than F, in which the F ratios for each univariate ANOVA and their significance values are listed. That's where I run it. The values associated with the univariate ANOVAs conducted after the MANOVA are identical to those obtained if one-way ANOVAs were conducted on each dependent variable. This fact illustrated that MANOVA offers only hypothetical protection of inflated type 1 error because there is no real-life adjustment made to the values obtained. The value of P equals 0.174, right here, tells us there was no difference between employee goal-setting groups in terms of task performance scores, but the value of P equals 0.009 tells us that there was a difference between employee goal-setting groups in terms of organizational commitment scores. Now we run the model containing the low correlation variables. Organizational commitment scores p-value of 0.009 tells us that there was a difference between employee goal-setting groups in terms of organizational commitment scores, but the p-value of 0.498 associated with employee satisfaction scores tells us that there was no difference between employee goal-setting groups in terms of employee satisfaction scores. While our multivariate test statistics reported that there was no significant difference between goal-setting groups for the highly correlated model, this tells us that for organizational commitment scores in the specific model, the type of goal setting used did have an effect. The reason for the anomaly in these data is simple because the multivariate test takes into account the correlation between dependent variables, and so for these data, it has more power to detect group differences. With this knowledge in mind, univariate tests are not particularly useful for interpretation because the groups differ along a combination of the dependent variables. To see how the dependent variables interact, we will carry out a discriminant function analysis later on. Now, the contrasts I created are not part of the MANOVA model, and so to generate the output for them, I have to create separate linear models for each outcome measure. This is basically the same as doing a one-way ANOVA on each outcome measure. Goodness, I'm sorry, I can't talk. My first model is based on predicting the variable employee satisfaction scores from group. Second predicts task performance scores from group, and third is based on predicting organizational commitment scores from group. I first look at the result of my contrast for employee satisfaction scores, which I see by using the summary.lm function, which reports the contrast parameters. So now I'm creating the models. Now I'm going to run it for employee satisfaction scores. The report tells us that when comparing no goal setting versus a combination of computer goal setting and pen and paper goal setting, right here, there are no significant differences in employee satisfaction scores, P equals 0.55. No significant difference in task performance scores, P equals 0.063. Which I see right here, 0.063. But there is a significant difference in organizational commitment scores, P equals 0.003. This means that there were group differences for organizational commitment scores. As to when we compare the group of paper and pen goal setting versus computer goal setting, there's no significant difference in employee satisfaction scores, which P equals 0.309. All the way up here. No significant difference in task performance scores, P equals 1.0, and no significant difference in organizational commitment scores, P equals 0.463, right there. Lastly, I follow each of my MANOVA models up using discriminant analysis. I could have chosen to just do univariate ANOVA or discriminant analysis, but for this assignment I'm doing both, which Andy also recommends doing. In discriminant analysis, we look to see how we can best separate a set of groups using several predictors. We are predicting a grouping variable from a set of outcome measures. So for my first model, I created with group as the name of the variable in my data frame that contains the groups that I'm trying to discriminate, and the highly correlated variables of task performance score and organizational commitment scores as my predictors. The LDA function from the mass package is used to create and execute the process. So now I'm doing it, and then I'm going to get the summary of it. The report shows me first the prior probabilities of groups, which is 0.33, because it is the group sample size divided by the entire sample size. And because the sample sizes of the three groups are equal, the prior probabilities are also the same for each group. Next, it shows the group means, but we've already computed them before running the main analysis, so we are not going to focus on them again. The main part of the output tells us that the coefficients of the linear discriminants are the values of B in equation. The coefficients tell us the relative contribution of each variable to the variance. We look at the first variant, which is labeled LD1, right here, and see that it represents something that differentiates task performance scores and organizational commitment scores. We see that they have an opposite effect because task performance scores report a negative number, while organizational commitment scores have a positive number reported. So the first variant differentiates groups by some factor that affects org commitment scores and task performance scores differently. For the second variant labeled LD2, we once again see that it represents something that differentiates task performance scores and organizational commitment scores because one reports a negative number, right here, and one reports a positive number. So once again, the second variant also differentiates groups by some factor that affects the two variables differently. So we're very interested to see if they're both positive, both negative, or one's positive, one's negative. Now I'm going to do my second model. That was highly correlated, yes. Second model. Now I'm going to report it. The second model I created with group as the name of the variable in my data frame that contains the groups that I'm trying to discriminate and the lowly correlated variables of org commitment score and employee satisfaction score as my predictor. When looking at first variant labeled LD1 right here, we see that it represents something that differentiates organizational commitment scores and employee satisfaction scores because one's positive and one's negative. So the first variant differentiates groups by some factor that affects org commitment scores and employee satisfaction scores differently. For the second variant labeled LD2, we're looking right here, we see that both reported numbers are positive, which tells us that the second variant differentiates groups on some dimension that affects org commitment scores and employee satisfaction scores in the same way. It's sometimes useful to look at the discriminant scores, which are the scores for each person on each variant. They can be useful because the variants that the analysis identifies may represent underlying social or psychological constructs. If these constructs are identifiable, then it's useful for interpretation to know what a participant scored on each. The predict function tells us each participant's score on the first LD1 and second LD2 variant as it pertains to the highly correlated model. Then we show a plot of the scores broken down by group membership using the plot function. The graph plots the various scores for each person grouped according to the experimental condition to which that person belonged. I did both these steps first for the highly correlated model and then for the lowly correlated model. So here's where we do the predict, then here's where we plot it, and that was for high correlation. Here's the low correlation. So this one's high, this one's low. It's very difficult to interpret, as you can see, because the variable names are overlapping so much, but I'm going to explain how I would have interpreted them if I could. To discover which groups variant 1 discriminates, we need to try to ignore variant 2, so ignore this one, which is on the vertical axis, and look at how the groups change as we move along variant 1 on the horizontal axis. So ignore the vertical position of each point on the plot and look at how the groups are distributed along the horizontal axis, all down here. You can picture a line being drawn vertically down the middle, right here. and ask yourself which groups cluster on either side of the line. We can then decide which groups the variate discriminates by seeing which groups appear on either side of the line. For the second variate, which is the vertical axis, we ignore LD1, which is the horizontal axis. So we ignore the horizontal position of each point on the plot and look at how the groups are distributed along the vertical axis. So we see if they're up here or down here. We do this by picturing a horizontal line across the plot in the middle and seeing which groups cluster on either side of the line. I would have done both of these steps for each of the created plots if I could tell, like if I could be able to read them. So LD2, you're seeing if it's up here or down here, and LD1, you're seeing if it's over here or over here. And thankfully, that is all I've got for you.